So, last time we looked at the fact that non-Archimedean valuation for number fields is given by a prime ideal, and towards the end we looked at some examples of completions. So, let me recall how you construct R. So, this is recalling from your analysis course, construction of real numbers. So, one of the constructions is using Dedekind cuts, but that is not the one that I am going to recall here. Another construction is using Cauchy sequences. Right. So, what you do is you consider R to be equivalence classes that A n is a Cauchy sequence, right, and then you put some equivalence relation on it. And what is the equivalence relation? If the sequence A n minus B n, this converges to 0, right. So, that is the set, and then you define. So, as a set it is this, and then you define addition, multiplication, you show that it is a field, right. Then define addition, multiplication, and prove that R is a field, right? And then you show that then you show that R has a metric extending 1 on Q, and R is complete with respect to that metric, right. So, this is kind of how R is constructed very briefly. Now, there is no reason why we can't do that with QP, right. So, now we can do a similar construction with p-adic metric on Q. So, I will do this for Q and then I will say that you do similar thing for number fields next time and give some details. So, what is the metric? Recall that on Q is defined as follows. So, you take x in Q minus 0 and you write x as p to the m times a over b, where p does not divide a b and m is some integer, and you define the p-adic valuation of x as p to the minus m. And this is one way of defining p-adic metric, and I gave it as an exercise to couple of lectures ago to show that this is in fact a valuation. And so, this defines a metric, let me call it d sub p, on Q, okay, all right. So, bunch of exercises show that Q is not complete with respect to this metric d sub p. What does this mean? This means that there exists a Cauchy sequence in Q that does not converge in Q. Okay, so this is exactly what we also learn with real numbers, right? If you take a decimal expansion of q of square root of 2, for example, you truncate it at any point, you get rational numbers, and so you truncate it at like after 5 decimal, 6 decimal, and so on. That becomes your sequence of rational numbers. That's Cauchy, and it does not converge to anything in Q. So you could try to come up with a sequence of a Cauchy sequence in Q that's Cauchy with respect to p-adic metric, and that does not converge. Okay. So here's an example of a sequence that converges with respect to p-adic metric, but doesn't converge in the usual metric, the Archimedean metric. So you can consider a n to be summation I going from 0 to n p to the power I, right. So a0 is 1, a1 is 1 plus p, a2 is 1 plus p squared, a3 is 1 plus p squared plus p cubed, and so on, right. So now if I look at an minus 1, this is p to the n, and what is dp of an minus 1? This is p-adic valuation of p to the n, which is p to the minus n, and this goes to 0 as n goes to infinity. Okay. All right. So, and you can check this with n and m, like an minus am. So hence the sequence an's is a Cauchy sequence in Q with respect to the metric dp. Okay. And in fact, an goes to 1 over 1 minus p, right. This is a rational number. So this is a Cauchy sequence that's not Cauchy, that doesn't converge with respect to the usual metric, but does converge with respect to p-adic metric, and it converges to a rational number. So it won't solve your exercise. Nevertheless, it's kind of a different sort of thing than what you have seen. Okay. All right. So okay, so you can define QP. So you can define QP to be sequences an going from 0 to infinity, Cauchy sequences with respect to dp, and then you put equivalence relation on this. So an is equivalent to bn if an minus bn converges to 0, right. So that's what Cauchy, that's what QP is, and then as with R, we define addition, multiplication, and prove that QP is a complete field. QP is complete, is a complete field. Okay. So I am not going to redo that. You can take this as an exercise if you like. This is a exercise in your basic analysis course where you learn construction of R. You can show that you can similarly construct QP. So that's one way of constructing QP. Now here is a more algebraic way of constructing QP. Yeah, okay. Before doing that, let me kind of see the following. So so you have Q, and then that sits inside QP. Now you can look at ZP, which is set of all elements in QP, such that is less than or equal to 1. Okay, so this on Q extends to QP. Okay, and how is that extension done? Well, you look at any Cauchy sequence and you just take limit as n goes to infinity of each of the thing, and you have to show that this converges, but this is exactly how you extend mod from Q to R. So it's the same thing. I mean, that's how this is part of the exercise that I gave before, right, that you have to show that it's complete. To show that it's complete, you need to define the metric, and this is how you define valuation, and then valuation would give you metric. Okay. So here is an exercise. ZP is a subring of QP. You have to show that it's a ring, and its ring structure comes from its being a subset of this field QP. Okay. And P times ZP, this is equal to set of all x in QP such that valuation of x is less than 1. Okay, this is a prime ideal in ZP. So that's also an exercise. So there are two parts to this exercise. Okay, so here is an alternate construction of ZP. All right. So what do I do then is the following. So maybe I'll give a third part to this exercise. So you look at Z mod PZ. This is isomorphic to ZP mod PZP. They are both, so ZP is a humongous ring. It has uncountably many elements, right? It's a huge ring, whereas Z somehow seems manageable. It has only countably many elements, etc. But when you take Z mod PZ, it's isomorphic to ZP mod PZP. Okay, and similarly, P to the n z mod P to the n plus 1 z is isomorphic to P to the n zp mod P to the n plus 1 zp. Okay. All right. So out of these so therefore, or actually, you know, you can write something nicer. Yeah, okay, maybe I'll just, so therefore Z mod P to the n z is also isomorphic to ZP mod P to the n zp. Okay. What this means is starting with an element alpha in ZP, we can construct a sequence of integers. These, you know, when you look at all these things first, it kind of may seem very confusing, or you know, even somewhat pointless, but you know, it either seems confusing or tautological, but you should think about this and work with this very carefully to understand it, because this forms the basis of whatever is going to happen in local fields, and so you should understand this very carefully. Okay, so what I do is I take alpha mod P, this is an element in ZP mod PZP, but this is isomorphic to Z mod PZ. So take alpha 1 to be any element in Z such that alpha 1 mod pz is equal to alpha mod pzp, right? And similarly we can keep going. So consider alpha n in Zp mod p to the n Zp, but this is isomorphic to Z mod p to the n Z, and so take any, maybe I am in trouble now because I wrote n here, I do not want n here, right. So take any alpha n in Z such that alpha mod p to the n Z p is equal to alpha n mod p to the n Z, right. And so I get a sequence alpha 1, alpha 2 and so on. And what is the nice thing about this? If I take alpha n and go modulo p to the n minus 1 Zp, this is same as alpha mod p to the n minus 1 Zp. Yeah, sorry, I do not want a p here, I just want a, I want this. But this is same as alpha to the n minus 1 mod p to the n minus 1 Z, okay. Hence, you can show if all these things are not obvious, you should think about them and actually rigorously write down a proof. This alpha 1, alpha 2 and so on is a Cauchy sequence of integers. All right. Okay, so starting with a Cauchy sequence, you of course get an element in Zp or Qp, and this is a way to go back. If you have some other way of describing Zp, you can get a Cauchy sequence out of it, right. So what I am going to do is I am going to describe Zp in some other way. So Zp is also equal to summation I going from 0 to infinity ai p to the I such that 0 is less than or equal to ai is less than or equal to p minus 1 for all I going from 0, 1, 2 and so on. Okay. All right. So that's a way to define. So this is, I'll give a few steps of this exercise, but what I am claiming is that this is an alternate description of Zp, right. So this is writing any element of Zp to the base p. So how do I get Cauchy sequence from this? So why is this? So let me give you some steps of this. So instead of calling Zp, maybe I will call it something else for now. Let me call it O, and then the exercise is that Zp is isomorphic to O. So what is the map? I want a map from Zp to O and the other way around, right. So let me define the map in the other direction first. So O to Zp, if I take summation ai p to the I going from 0 to infinity, I want to get a Cauchy sequence out of this, right. So I want some Cn's, and what is Cn? Summation I going from 0 to n ai p to the I, right? This is an integer, and then the claim is that this is a Cn is a Cauchy sequence, and you have a map like this, right. And you can go in the other direction as well. So, how do I go in the other direction? So, map in the other direction. So, I am just giving you some steps for doing this exercise. So, I have a Cauchy sequence Cn. Yeah, so this is somewhat tricky. Yeah, so instead of doing it like this, what I am going to do is I am going to take this alpha and then send it to first alpha to the n as before, right, and then each alpha to the n is summation ai p to the I going from, sorry, not here, where am I writing it, I going from 0 to n, right, and then formally I can just write this as alpha prime equal to summation I going from 0 to infinity ai p to the I. So, this alpha goes to alpha prime then, right. So, let me not put this arrow here, but let us say I get this out of it and then I send alpha to alpha prime. And so, your exercise would be to show that these two maps give inverses of each other and they are ring homomorphisms. Okay. So, this is another description. So, hence ZP can also be described as summation this set I going from 0 to infinity ai p to the I, where 0 is less than or equal to ai is less than or equal to p minus 1 for all I bigger than or equal to 0. And if you want QP in this description, this is summation I going from minus n to infinity ai p to the I such that 0 is less than or equal to ai is less than or equal to p minus 1, I is bigger than or equal to minus n, and n is just some natural number. Sorry, this is QP, not Q. So, this is another description of QP. Okay. Now, there is a third description of ZP. This is more algebraic and somewhat more sophisticated. So, I will describe this, but I will try not to use this much. So, you do not need to concentrate on this too much, but it is good to know about this. So, let me just, I am not going to define the notion of inverse limit in general for you, but ZP is inverse limit over n of z mod p to the nz. And what does this mean? So, what you do is you take this is a subset of product n greater than or equal to 1 z mod p to the nz. So, this is just a Cartesian product. So, this is usual thing that you learn in set theory, but how is this, what is this subset? So, how is this defined? This is, so En in product n greater than or equal to 1 z mod p to the nz, such that if I take An modulo p to the m, right. So, for any n bigger than equal to m, if I take this, I simply get Am. Okay. Right. So, the way to think about this is I have A1, A2, A3 and so on, and this is in Z mod PZ, this is in Z mod P squared Z, this is in Z mod P cubed Z and so on. Here an, this is in Z mod P to the nz, and there are maps in this direction, right. There is a map like this, there is a map like this and so on, and under this map an goes to n minus 1, an minus 1 goes to n minus 2, etc. Okay. There is no restriction when you take Cartesian product on what the coordinates will be. They can be arbitrary coordinates, but when you are taking inverse limit, they can't be arbitrary coordinates. So, it is a very specific subset of this Cartesian product which satisfies this property that if you take an mod p to the m, then you get am. Okay. So, this is another description of ZP, and I am not, as I said, I am not going to use this too much. So, I am not going to dwell on it or give you isomorphism from this to the first two definitions of ZP, although using this description where we get alpha n's out of alphas, it should be very easy for you to construct this isomorphism. So, if you are interested, you can try to do it for yourself, but I will try not to use this at all. So, you do not need to worry about this third description. Okay, so we saw QP as a p-adic completion of Q in this lecture, and we saw a few descriptions of how to think about QP, elements of QP and elements of ZP. The more you work with it, the better you will get at it. So, you should try to compute things in p-adic integers, do exercises etc. from textbooks about p-adic numbers, and you will get more comfortable with this. So, we do this because we want to do analysis with p-adic metric, and in fact analysis with p-adic metric is actually just algebra in analytic language. So, in fact it is much easier than real analysis, and that is why number theorists really like p-adics, because you can use a lot of ideas from analysis, and often it turns out to be easier. So, having seen these p-adic completions of Q in a very explicit way, next time we will look at p-adic completions of number fields. They will be less explicit than this, but if you get very comfortable with QP, then you should not have a problem with working with completions of number fields. And then we later on we will see that completions, p-adic completions of number fields in fact turn out to be finite extensions of QP, p-adic completion of Q, and so we can study Galois extensions of number fields using Galois extensions of QP. So, that is going to be our direction for future few lectures. Thank you.